Okay, so in this video we're going to be talking about the chain rule. This is Unit 2, Part 2, Lesson number 3 for our calculus class. The chain rule was discussed on number 25 in our derivative list. And what I want to point out here is that this chain rule is really useful for what we call a composition of functions. And you may remember this notation from your Algebra 2 days or even in college algebra last year. Anytime we have a function composed with another function or a function inside of another function, we're going to use the chain rule. The combination with multiplication and division, that requires the product in the quotient rule that we talked about in the last video. So again, a combination is when we simply multiply, divide, or add and subtract. But we can combine functions together or we can compose functions together. And it's this composition that's going to require the chain rule. Now the theorem and the definitions that go with the chain rule can be a bit confusing. I think we can learn these better by maybe having this discussion in class next time we see one another. And instead, we're just going to do some practice problems to hopefully reinforce the concept. Most of the time, I use the version number 2 or style number 2 when using the chain rule. Although version 1 makes good sense if you're comfortable with Leibniz notation for derivatives. Okay, Leibniz notation is what's being done up here, and Lagrange is what's being used down here. And this is what we use mostly in our class, is this Lagrange notation. The way I describe this to my students is that we need to take the derivative of the outer function and we leave the inner function alone. So you'll notice we've got derivative notation on f, which is our outer function, and we have no derivative notation right here on g, which is our inner function. So the derivative of f, we leave the inner function alone, and then to compensate for the behavior of that inner function, we multiply by its derivative at the end. So let me show you what I mean here with example A. If my objective is to find the derivative of y, I would label it like this, dy dx. I'm not using y prime just because. I could just as easily say y prime, and that would make sense. But dy dx, the derivative of y with respect to x, I need to find the derivative of the outer function, and I leave the inner function alone. Well, in my mind, I see this outer function as something, and I'm blocking it out right now, but something cubed. X cubed is kind of like this outer function here. And what would the derivative of that outer function be? Well, the derivative of that outer function is 3 times that variable squared. Now, I'm not writing anything just yet because I don't want to write x here. We're not talking about the derivative with respect to x yet. We're finding the derivative with respect to that inner function. So 3 comes down to the front, reduces by 1 to make 2. So 3 times something squared. The instructions did say to leave that inner function alone. So I'm going to write 5x plus 4 on the inside. Now, immediately after taking the derivative of the outside with respect to the inner function, we turn around and multiply by the derivative of the inner function. So now I need to multiply by the derivative of this guy on the inside, which happens to be 5. So our derivative, if we clean this up, and this one should be cleaned up because the multiplication here being commutative is easy to perform. So we'll multiply 3 times 5, and we'll end up with 15. The 5x plus 4 squared wouldn't be too bad to expand that binomial, but you can imagine that if this was, say, a power of 100, we probably wouldn't expand that. So let's not get in the habit there. We'll leave this answer as it is. For part B, we have the function y equals sine cubed of x, and if you recall, with trigonometric functions, the derivative, the function sine cubed literally means sine of x, that function raised to the 3rd power. So here again, our outer function would be perceived as something cubed. And in using the chain rule for derivatives, we would say that y prime or dy dx, either one of those notations are fine, is the derivative of the outer function, 3 times something squared, with respect to the inner function, keep that inner function alone, times the derivative of the inner function. Have you been memorizing your derivatives? Do you know what the derivative of sine is? Well, the derivative of sine is cosine. Make sure you're memorizing those derivatives to help you with this work. Here again, I think we can clean this up just a little bit. Out of habit, I would write 3 times cosine x first and then multiply by sine of x squared. To keep in line with the format of the equation as it was written originally, we might write 3 cosine x times sine squared of x, and that would be appropriate as well. Now part C is just a little bit different. This notation, sine of x cubed, implies that there's a grouping symbol around the x cubed. And now what's interesting is that x cubed becomes the inner function. That's the one that's wrapped inside of our grouping symbol here. So x cubed is our inner function and sine is our outer function. So the derivative of y, or dy dx, would be equal to the derivative of the outer function, which we said was cosine, with respect to the inner function. So we keep the inner function as it is, and we multiply by the derivative then of the inner function, which is 3x squared. For notation purposes, I do like to bring the 3x squared out front. We have cosine of x cubed that remains. And that's it. That's our chain rule. Now I'm being sarcastic here. The chain rule is quite complicated, or can be quite complicated, especially when we get into some more challenging problems. What I'm going to do next for this video is just to reinforce how the Leibniz notation, or version number 1 of the chain rule, can be used. And I think I forgot to press record there, so let me just back up and try to catch where we left off. So the outer function, u cubed, its derivative with respect to u is 3u squared. The letter u was used as our variable, so that's going to be the letter that's used in our derivative. The inner function u was 5x plus 4, and the derivative of this function with respect to the variable x is just 5. The definition, using Leibniz notation, says the derivative of y, the outer function, with respect to x, the variable on the inside, is simply equal to dy du, the first derivative, times du dx, which is the second derivative. Not a second derivative, but the second function's derivative. So again, dy dx, which is what we're after, is equal to dy du times du dx, and that should, in a sense, be clear to you, because if I were to multiply these fractions, the du's would cancel and we'd be left with dy dx. dy du happened to be 3u squared. Du dx happened to be the number 5. So here is our derivative with respect to x, but the problem is this letter u isn't the letter x. It's not the variable x that we want to report this as. But we did define u as 5x plus 4, and so there's the function in terms of x that we were after, 5x plus 4 squared times 5. And then, as we did before, we can multiply the 5 and the 3 to clean this equation up, to simplify it just a little bit. And we've got our 15 times 5x plus 4 quantity squared, which is the same as what we got before. So a little bit more thought that goes into that, but the definition is a bit more straightforward. Let me try another example and see if it makes sense to you. For part B, our outer function is going to be u cubed again, so I'm going to call this one y equals u cubed. Therefore, the derivative of y with respect to u is 3u squared again. The inner function is sine of x, and the derivative of u du with respect to the letter x, or the variable x, is going to be cosine of x. And to find dy dx, I multiply these two together, du dx and dy dx, I'm sorry, dy du. So I've got 3u squared times cosine x. Once again, we don't like the letter u because that's not the variable in question. So I need to change that x, I need to change that u to some combination of x, which happens to be 3 times sine of x. This u value was defined as sine of x, so I'm making that substitution. And as we've seen before, in the red ink above, a nicer way to write this would be 3 cosine x. This product can be brought to the front, times sine squared of x. Lastly, in this example, we said our outer function happened to be sine of x. So the derivative of that outer function, let's call it sine of u, not to mix up our variables here. So the outer function with respect to u, so sine of u, its derivative would be cosine of u. The inner function we said was x cubed. So the derivative of that inner function with respect to x is 3x squared. When I multiply these two together, I'll end up with the derivative of y with respect to x that we're after, which happens to be cosine of u times 3x squared. And to replace the u variable with the x variable, we'll have cosine of x cubed times 3x squared. More appropriately, this would be written as 3x squared times cosine x cubed. So certainly I expect some questions on this approach. Please send them my way and I'll try to record a response for you. Otherwise, you can bring them to me in class if you happen to watch this before we meet next. Thanks for watching.